good morning. Wired, crossed with design, crossed with Skywalker, out of this world. We're thrilled to be here. So let's take a journey from Earth to Mars, if you'll allow us. Imagine all the world leaders in the United Nations looking out the window and seeing Spaceship Earth, coined by Buckminster Fuller, the Renaissance engineer, designer, architect. He had the pleasure to have him as an advisor for his lunar base colony. Bucky's vision was that we would make different decisions, important decisions, if we saw the world, the Earth, as our own blue dot, our own spaceship, and if we could see war, famine, hunger, and celebration and music, but we would see it very holistically. We would see Earth in its entirety. This morning was a beautiful sunrise, but maybe not as beautiful as Earthrise from moon. I'm a rocket scientist, an engineer, and I have the great job to work with great students, and our goal is simply to design the world's best spacesuit so we can get people to Mars. It's been a great collaboration that I'd like to tell you about. Have to understand the current spacesuit. It's fantastic. It's an engineering marvel. It keeps you alive, gives you oxygen, scrubs out your carbon dioxide, gives you the pressure that you need to survive in the vacuum of space. Beautiful, wonderful, but it's kind of big and bulky and heavy, so we have some great design challenges just waiting for us. We've been working on them for a couple decades. 45 years ago, the Apollo suit, again, a phenomenal engineering feat. But couldn't get a lot of science done. 1/6 gravity of the moon. So you're really light, you're low, but just can't reach down there to get my scientific pack. We'd like a little bit better locomotion. This bunny hop, we'd like to give you natural motion. So a little hard to get our exploring done. Again, great for 45 years ago, but we can do better. That's our challenge. The current suit today, this is astronaut Katie Coleman going for a training run underwater in NASA's Neutral Buoyancy Lab, the world's largest swimming pool at 6.2 million gallons. So you dress up, it's 140 kilos, that's close to 300 pounds, gas pressurized, and you're really fighting, and you have to move the suit. So you're wasting probably 75% of your oxygen just to move this suit. I'm going to introduce you to 3 different design concepts. So 3 suits. First, the gravity loading countermeasure suit, kind of called the blue suit. So one-handed push-ups are great when you're really in a microgravity environment. We're flying on the NASA plane. This is a compression garment. So it's loading from the shoulders down to your feet, compressing you, recompressing you, because you actually grow a couple centimeters when you get into the weightless environment. You have a lot of muscle loss, 30% muscle atrophy. That's the good news. The bad news is the bones, 1 to 2% bone mineral density loss per month. Now who wants to go 6 months on station? We have a 1-year mission coming up. So our designs for these compression garments this is an exercise countermeasure inside the vehicle, but to really help the astronauts stay healthy and well as, you have to do this in parallel with exercise, rowing and on a treadmill. To the left, you see a little fellow. We're using our same design technologies, the materials and the design for little folks with motor control disease right here on Earth. This little fellow has cerebral palsy. Can we help his daily activities? Just help him step, help him walk, help his motor control just be a little bit better so he can enjoy just daily activities of being a fun little 6-year-old. We're working on it. We still have a way to go. Second suit I want to tell you about is a suit within a suit, if you will. So developed and designed the technology for the current systems, for the current gas pressurized suits. Again, they're fantastic, but they're so big, they're oversized, and there's a lot of injuries. Matter of fact, we have, from the shuttle and station astronauts, 25 shoulder surgeries, injuries from training, going underwater, doing all of that training, 12 hours of training for 1 hour of space flight. So what was the design innovation? How could we help? Well, maybe we could map the human motion. Where are those injuries potentially going to take place? And then could we do something about solving it? So we've come up with a suit within a suit that I'll show you part of, called the octopus. I'm wearing it. And we developed these pressure sensors so that we can get that map, if you will. So these red sensors all over, these little sensors here. See why we call it the octopus. It straps on. So as I move and as I make contact with the suit, then these pressure sensors are giving me that map, and they're showing me what the force is. How do we do it? Well, these are actually microfluidic channels. You push on them, get very high resolution pressure sensing kind of over the whole body. It's a collaboration with Rob Wood's lab at Harvard University. This is a great MIT and Harvard collaboration. How does it work? So we did strap it on, the subjects, put them in the NASA Mark III suit. This is down at Johnson Space Center in Houston. And let's take it for a roll. Trying to get maximum mobility, trying to measure, again, how I'm moving and then how I'm going about moving the suit. And how much energy is all of that taking me? Maybe, like I said, maybe I'm wasting a lot of energy just trying to move the suit. You see some sensors on the outside of the suit because we're also measuring the outside motion. Better than the Apollo suits, but we still have a long way to go. Oh, the students love that. They call that the reverse Macarena. So it's wired. You guys, no one's afraid of data here. So this is from 6 different sensors. And what you're showing is as I make contact with these different points, then it goes along. So we can see here's maybe where injury is. This is what the force is. So we can really quantify now for the first time. It's kind of our eyes inside the suit. So real high point here on the forearm, underneath the arm, because I have to move the arm of the suit up. Now I reach across, and so there's a point right here of pressure. Move over here. So again, just kind of really looking at the detailed and this map and what the pressure levels are and will they cause injury or not. And then the final phase of this design is actually how can we do something about it. This is actually a collaboration with GE. This is their latest prototype, GE working with Dynasy and industrial designer Michał Krasic from Poland. So how can we actually protect? It's an active system. It's kind of like airbag technology, but you're wearing it and protecting your shoulders. It still gives you all the mobility you need, but it's really wonderful 3-dimensional materials that, again, it sizes. I need about 4 centimeters to take up the room in the suit, but someone else might just need 1 millimeter. So it's all very custom fit, and we're hoping that this can dissipate the energy, and we'll be testing this in the NASA suit coming up in early 2015. Moving on to the third suit, the Biosuit, which you see here. We have a mock-up to show you, and I'd like to tell you a little bit about that. Design-wise, we thought, clean sheet design. All these gas pressurized suits, it's all that we've ever done. It's all that we've ever known for NASA and the Russian program. Everyone has been in a gas pressurized, 140, close to 300-pound suit for microgravity. It just won't cut it when we get to Mars. Why Mars? It's challenging. It's pretty far away, but it does make sense in the future to send humans and rovers to Mars. We have 5 current missions to Mars right now. The rovers are vehicles. 3 of them are on the surface, getting us a whole bunch of scientific data on Mars. We just landed last week in an orbit of Mars, MAVEN, from NASA, and the Indian Space Agency is now orbiting Mars too. So we know a lot about Mars, the radiation and the environment, and how to work on Mars, and it is challenging. Olympus Mons is right here in the middle, second highest volcano known in the solar system, 3 times Mount Everest. So for all you climbers out there, there's still more challenges in the solar system. And Valles Marineris, the Grand Valley of Mars, Grand Canyon, no. Valles Marineris is 10 times the length of the Grand Canyon. So we have some extreme exploration to do. How do we think we're going to do it? Well, the Biosuit then says, we're not going to go with the gas pressurized system. We still need to pressurize you. It's the pressure layer, so it's mechanical counterpressure. I'm going to squeeze you. It is literally a second skin suit. So we're going to put the pressure directly on your skin. We have to create 1/3 of an atmosphere. So we'll create 1/3 of an atmosphere, and then how do we do that? We actually do that through both the material properties and the design. If I'm really interested in how do I get maximum flexibility, how I'm going to rappel up this mountain, Olympus Mons, how can I have maximum flexibility and not be restricted? Well, we look at the body. We study the body. And matter of fact, for an aerospace engineer, I know way too much about the skin. So as you're moving, if you drew little circles all over your skin and moved around, lots of those little circles would turn elliptical, like the animation playing. So there's 2 red lines, those bisecting diameters. From the circle to the ellipse, they pivot, but they do not extend. They're very special, little bisecting diameters. If I connect all those red dots, it's really just the mathematics. We actually get this suit. So the black lines here on this suit. So if we do that, again, we're looking at the basis of kind of a second skin, and it's a kind of a soft exoskeleton. If we can do that, I can have enough structure of the suit, but I can get you maximum mobility. So that's the patterning, and then the materials, we're always looking for advanced materials as well to get us to pressure production. So we've hit our targets just recently with using some shape memory alloys, some active materials in concert with the design and the patterning. And then lately, we've also have a brand new helmet to introduce you to. So introducing Guy, my partner and soulmate, tell you about the new Biosuit helmet.
Hey guys, good to be here. It is wonderful to work with this lady, let me tell you. And the latest part of the Biosuit is working on this helmet. We're spending a lot of time trying to make it lighter. I mean, Dava is the leader, designer, constantly make it lighter and thinner, so this suit eventually probably be as thick as our skin. The idea is to make this helmet, as mobile and visible as possible. The changes are great compared to what the NASA present suit is. And this one, you move your head with it. We increase the visibility because we want to do exploration or you want to work with your hands. We still have visors to add, as you see in the image. We have a bar where actually we'll attach tools such as videos, equipment, scientific equipment, and so on. So I've been working on this thing for about 35 years in the space business. Since I was a student, I became injected by the virus of space, and as an architect and designer, basically has veered my life totally to another world where I thought I was going. And this started literally in 1969, arriving in Houston a few weeks before the Apollo landed on the moon. And since then, and as an architect, I wanted to work in space. I was down the street, I went to NASA, and eventually got involved in the lunar bases and many of the designs that you see up here. We were working at the time on glorious projects of very large space stations where we would have colonies in low Earth orbit, colonies on the moon. It's taken a long time, but today we have an incredible laboratory in space. This is our space station. This is a place where astronauts work every day of the year. We have 6 to 9 astronauts constantly there, experimenting, living, learning. This thing is about over 100 yards long. It's longer than a football field. So I had the privilege of spending about 10 years working in the interior of this hardware. Looking at really the human factors, how humans will live here, how humans will eat, sleep, and all of the habitation aspects of it, the human factors. I mean, you're designing for an environment that you don't know anything about. So we spend a lot of time flying on this NASA plane, the Vomit Comet, as we call it. And then a lot of time underwater. So we spend in neutral buoyancy. This is a galley. The space station is designed with these modules. So we have about 3.5 of these modules to pack food, to store it, to freeze it, to refrigerate it, to prepare it. So we went all the way from the design of the packaging, how do you actually store these things. And in space, you don't have, particularly without zero gravity, without gravity, you don't have convection. So really creating an oven, the oven was a beautiful design to make it work, the beginning of really injection heating and so on. So we spent a tremendous amount of time really working on full-scale prototypes, actually building these things and testing them with astronauts. And the other part that I'll show you today is the sleeping quarters, where we spend time designing the sleeping bag that restrains you and holds you. We talked a lot with astronauts about how they would like to sleep, and some of them just float around and they sleep right here and wake up over there over the roof. And you can travel, because the air pushes you around. So in Skylab, the first space station, people would sleep this way because there was only 3. Now it would be difficult with all this, too many guys hanging around. So we worked on this space, creating the most private space. We took care of acoustics, lighting, communications, safety. So this is your personal space. So what is next after the space station? We're talking about probably 2025 is when the space station, basically the life of the space station will be. But the next step would be to go to Mars. This is what we're working on, the suits and so on. But before we go to Mars, we have to learn our lessons. Mars is about a year away from here, and a year there and a year back. So you need to design systems that are totally reliable where they will last. You know, you can repair them, but you cannot exchange them. You cannot ask for help. So therefore, the lunar surface is really the place to go to test and learn about how we might live one day on Mars and starting to live on the moon. There are many reasons to go to the moon. The moon is really has a lot of oxygen, believe it or not, contained in the soil, a lot of metals, a lot of glass, a lot of materials that we can use both for construction of vehicles on the moon or to make an atmosphere, to create propellant. You know, oxygen is our propellant to go to Mars. So maybe it becomes a propellant depot. The challenge of the moon, obviously, is that you have a reduced gravity, so in many ways it helps you. But on the other hand, when I was working with Bucky Fuller, actually spent time thinking about how we anchor these things to the soil and the rock of the moon. The forces were so great, so we worked on a lot of different geometries of how to make this inflatables. And inflatables are really the way to go. We're working right now on inflatables, and we're actually will fly inflatables to the space station as additional modules. So it's really cool, the development of the new fabrics, the new materials that allow us to do this. So the vision now is actually to, instead of actually build a stationary base, if exploration is mobility, I mean, to explore, it means that you're going to be running around the moon and exploring these mountains or Mars and these canyons and picking up samples. So we're looking at the potential, and this is a proposal that we're making to NASA, to actually explore the moon with these rovers. This is an early rover, the Apollo program, that it gave them a huge range of away from their module. But our proposal right now is to have these vehicles, 2 of these, that would take 4 astronauts each. So you have a crew of 8 guys traveling on this kind of Winnebago of the moon. It has that manipulator arm that can actually pick things up and bring them in, and so we can experiment without having to go out. You could go out if you need to. And so this has an incredible suspension system. I'm not going to bore you with all the engineering, but if you look at this thing from the top, it has all the air and water tanks. So with this manipulator, you can actually exchange them as crews exchange this is like taking a cruise. You know, crews go in, crews going out. So and it has the solar panels and the radiators and all these things. And the interior basically is 4 workstations where you live and work, and it has to house all of our needs. You know, the hygiene, you name it. You know, food and so on. The same as the space station. These Scorpions actually have this pneumatic structure, inflatable structure that would expand and contract. So when they're camping and the 2 of them come together, they can mate and actually have this tunnel, this environment that will serve as a workshop or a laboratory or a place to play. So this is really our now the proposal, the idea of actually mobility on the moon, and maybe that's the way we should go to Mars. So we're using the Antarctic as an analog right now for some of these planetary missions. There's already a base in the Arctic and some in the Antarctic. I had the pleasure and privilege to work in the South Pole. We won a national competition for the design of the South Pole Station. And the reason I think we won it is because we're really thinking space. We're really thinking isolation. We're really thinking about extreme environments, people living in a very dangerous environment. It's really strange when you land there and the plane leaves. You know, they can't turn the engines off because it freezes, it won't come on again. So, you know, you're left there with your bags and this thing leaves. What we learned really is to design for the environment. We're looking at, you know, aerodynamics. The wind in the South Pole blows always from the same place. So this becomes like a vehicle. This is actually what it was built, but we use that as a great analog. There's a lot of experimentation going on there. And then I want to leave you with our last story that is our own story that we circumnavigated the planet on our sailboat, and basically to teach children about technology and exploration, And this is the route we took. We took basically went around the world from Boston to the equator, and then just went around it as close as we could to the tropical areas of the planet. We met really some fantastic people. We had a couple of projects that we worked with in terms of creating maps. We asked all the kids to make maps, and it was really wonderful for you graphic designers, because the maps always place themselves in the center of the earth and in the front of it. So we have this fantastic collection of kids' maps where it's like a picture of the earth taken from all the different spots. The other one was oral history, where we asked kids to ask the same questions to their friends, their parents, their grandparents, and people in their community. So, like, what is the technology that most influenced you? It was really beautiful to see the differences just, in the 3 generations. So we have a beautiful collection of that. So anyway, we were supported by NASA on this project, and we basically had this video conferences that we had in every place where we could do it around the planet, with high schools, local high schools. Then we connected a high school in the United States in many different states, and then an astronaut at NASA. So we had 3-way conversations, and it was really wonderful to see the conversations anywhere from what jeans you wore to what music you heard, and in addition to all the science and technology. So
it was a great trip. We survived, so we're back. We wanted to leave you just with one image. Again, from all of our exploring off-planet, back to Earth, it always comes back to the human condition and the human spirit. Thank you for your attention.
Thank you.